Okay. Hi, everybody. We continue our work illustrating interesting applications by using control design and simulation toolkit and by using Kalman filter. In this lecture, I am going to illustrate to you two interesting VIs. This is the first one here. The block diagram illustrates how we can create an estimation model, then converting that model to simulation VI, and at the end using this VI with the discrete state space in order to estimate the value at the input, which is considered as an input value to Kalman filter. Here we do not have a Kalman filter. We have Kalman gain.vi. But we use Kalman gain.vi, and the gain of the Kalman filter, the Kalman gain.vi, is fed as estimator gain L for the control design state estimator VI. Remember, in one of the previous lectures, we have worked out similar example where we found the control design initial trajectory VI in this lecture. We shall do the same with the addition of the simulation VI of the estimator itself. Let us work on it step by step. So at first we construct a state space model. Let us show you its label. We have constructed a state space deterministic model. The values of the matrices A, B, C, D are given in the front panel. Here they are. This is the A matrix, B matrix, C matrix, and D matrix. The response here, this is the model itself. The model is fed to step response VI. Okay. Control design step response VI. This is the VI. And at the output, I have created an indicator which shows the step response graph. This is the graph. As you see, the graph represents a system with a polynomial output, and the degree of the model is, of course, 2, as we have 2 rows and 2 columns, 2 by 2. This means that the system is having two variables. Anyhow, we can decide about that without looking at the matrix itself. I can have the model itself. As you see, this is the state space model. I converted the state space model to a transfer function model at the output. And I found again the response, the unit step response for the states, for the transfer function. And also I have drawn the equation which represents the transfer function here. If you look at it here, you can see that in the denominator, S is to the order of 2. This is Laplace variable, complex variable S. So we have two roots here. And also, as you see, we have two zeros in the numerator. So this system includes two zeros and two roots. And also, to be more sure, you can find the location of these poles and zeros by using the control design plot zero map VI. This is zero map VI. This is the output or indicator which shows the locations. If I double click it and see on the block diagram here, this is the complex plane. This is the imaginary line. This is the real axis. And here we have 1, 2 poles. They are red axis, as you see. And both of them are lying in the left-hand side of the imaginary axis, which means that the system is stable. We have also other two circles in blue here, which represents the zeros. Okay, so going back, we have created a state space model, deterministic one. We have checked its response to a unit step, and we found that it is exponential. Practically, it is exponential. We also checked the location of the poles and the zeros of the transfer function, which is equivalent to the state space model. Also, I have taken the state space model and used get system dimensions, control this VI here, get system dimensions VI. Where it lies, I can go to the control and simulation, control design, model construction, and here is the model information. The subpalette here gets system dimensions VI. This VI, which I have used. Get system dimensions VI. Why I have done this? Just to show you how many inputs we have, how many outputs we have, and the number of the states. If you examine at the front panel, you will find them here. We have one output, number of outputs, number of states. We have two states, which is true because we have two roots, as we have seen on the block diagram. And the number of inputs, we have one here. Let us put them together, maybe more interesting. Yes. So we have one input, one output, and two states. 2 rows by 2 columns means 2 states. Having that, now we shall change the continuous deterministic state space model to a discrete one. In order to have that, you just use this VI here. This is a conversion VI, and you have to fix the sampling time, which is suggested. I have suggested it to be 1 second. So this output here is the model itself of the discrete state space model. Look, the structure of it is exactly as that one of the continuous model, but the sampling time is given as 1. Okay, now this is a requirement for the Kalman gain VI, so we supply this discrete state space model to Kalman gain VI. Remember, we have said that we usually need to connect to the Kalman filter gain 3 matrices: the process error covariance matrix Q and the measurement error covariance R, in addition to the mapping array here G. These things are shown also in the front panel. This is a Q. As you see, it is 2-dimensional because we have 2 states. This is R, the value of R. Really, I have taken the values of Q and R as the initial suggested values by LabVIEW, but you can change them upon request. This is the mapping matrix G. It is a unity matrix. The diagonal values are 1, 1, 1, 1. Reminding you also with the important thing here that to work with Kalman filter and Kalman filter gain, you need to guarantee that the state space model is observable. So we use the control design observability matrix VI. We supply the state space model and check if it is observable or not. The answer is yes, as you see here with the light green. It means yes. If I run the program, now it will light green, meaning that it is observable. Now we have Kalman filter gain. We connect Kalman filter gain to the control design state estimator VI and get at the output the estimator model. Here we can use the estimator model itself with the control initial response VI or the control initial trajectories VI. I didn't repeat the trajectories because we have seen them in the previous lecture. No, they are here. They are shown. Now let us go and be sure. So here we have the real or true state variables. As you see, they converge to a value around between 0 and 1, which means that the system is stable. And the other graph here shows the states of interest, which are two of them are the estimated states, and the other are the original. So the original ones here, which begins with 0 and 3, this is one which begins with 0, and this is the one which begins with 3. This is a repetition done by the program. And here the other two states of interest which are going to be estimated. I have defined the initial values by of 0 and 5. If you go back, here 0 and 5, 0 and 3. So now we have the estimator model. Now we cannot use the estimator model to show how an external input looks like as an output of this system. We need to convert the estimator model by using convert control design to simulation VI and feed this simulation VI to a discrete state space. How to find the discrete state space? It is not difficult. You right-click the control and simulation loop, go to simulation palette, and here at the discrete linear systems, you find the discrete state space. This is the function which will be connected with the simulation VI here. So the simulation VI is connected with it. And now, if you apply an input here, you can find how the output will look like, taking in consideration, of course, all the data and conversion which has been done before. Let us try two options. One of them to have a unit step here. Again, go to the simulation palette, signal generation, signal step. Here it is. This is the signal step as of step signal as it is here. Now I can connect it directly to the input here. This is the input. If it is not well seen, you can go to the help here, show context help, and put the cursor on it. You will see it is here. It is the input UK. This is the input, the unit step input. I added to it a very small value of noise just for generality, but this is the input here. And I have multiplied this input value with a scalar as I want, and I will get the output as a unit step. If I go to the front panel now, here is the scalar to 1. If I run the, now let me clear it for you. If I run the program now with this input as 1, the output will be around it. It will be 1. It is about 1 now, and now it will settle to 1.01 as you see. When it is practically has established this value, yes, it is. So it is here shown 1.01. The error of estimation is 1%. We can change the input to be any function. I have created a signal, a sine signal here. Instead of using the step unit here, you can put or connect the sine. Now, if we go to the front panel, and run the program, we shall have a sine wave. Of course, with a simple limited error, it is about 1, as you see. If I stop it anywhere, here it is about -1. If I run it again and stop it, here it is. No, what is going wrong? Not yet. Let us go. Now it is okay. It is around 1. Here around -1. If you want to increase the amplitude, you just use the multiplier here. For example, to 2, and run it again. Now you shall have an output around 2, the maximum. Here it is -2. If you run it again and stop it, again in the minus side, I wanted to show you from the upper side also. It is about 2. If you want to 3 or 4, let us make it 4. For example, run it again. It is 4. So the system is working. So with this program here, we have created an estimator model by using control design state estimator VI and Kalman filter gain. And this model now is converted from state space to a simulation VI and used with the control and simulation loop to show the response for a given input. Okay. With this program I have finished. Let us go and consider another interesting program. Here it is. Now LabVIEW will open and I shall illustrate it for you. So what does this program represent? It represents a Kalman filter, discrete Kalman filter, which is the most common and commonly used version of Kalman filters. Remember, we have talked about the configuration of Kalman filter. We have said, let me show you again, that, okay, we go to the simulation, for example, to the discrete Kalman filter. This is the discrete Kalman filter. If I double click it here, as you see, this is the configuration page. I can configure the values of the matrices. This is A or phi as given here. This is B, this is the C, this is the D. This is the G and H scaling factor, scaling or mapping matrices. So the values and the dimensions of these matrices are configurable and could be configured in one of two ways, either by using a terminal, and this, I click the terminal here. Now it is ticked, and then there will be now if I say okay, I come back here. You see that here a red terminal appeared. Stochastic state space model. So I have to connect to this terminal the stochastic state space model. Also, this applies for the noise model or statistic noise model. In LabVIEW, you have the option to configure Kalman filter internally, either by using the already furnished configurations and changing the values and dimensions upon request, or by using an external terminals. Two external terminals usually are needed. In this example here, I am using this Kalman filter, discrete Kalman filter. I have used the terminal option and connected to the upper one here, the stochastic model, stochastic state space model. This is the discrete stochastic state space model. And the other input is for the second order statistic noise model. Now, how to get them? So at first, as you see, I have created a state space model as usual. I have examined this model to find the number of the states, number of inputs and outputs, as we did before in the previous example. We used for that get system dimensions VI. Also, I have examined the response. As you see, the step response and the state trajectory. This is the true state trajectories. You can have a look at them. This is the state trajectory graph, and this is the external, the response for an external unit step. And you can see that it is an exponential, and the system is, as you see here, we have a wrong arrow, cracked, showing a wrong thing because we have discrete Kalman filter here not connected. I take it away now, the system is working fine. So now I have also examined, I have taken the matrix A and find the eigenvalues for it, just to be sure that the system is normal. Then the continuous state space model is converted to a discrete one. And here is the converting VI. I have decided the value of sampling time. And now the output here is also converted to a stochastic space model from discrete or deterministic to stochastic. And now this stochastic output is fed to the Kalman filter. Why it is converted to stochastic? Because you know that the virtue of Kalman filter is it's filtering the data which is inserted to the control system randomly, yes, and makes the reading more accurate. The feedback which comes as y of t, here is the feedback signal which comes from the system. Here it is simulated. The output, now I shall talk about it for you again. And the input u of t also, both of them are fed to Kalman filter, and now it gives an estimation. This estimation is very accurate, specifically when you have a stochastic state space model or stochastic system. Now, in order to work well and standard approach, I have used or converted the state space model here to transfer function. Now we have here a transfer function, and now we created a discrete transfer function to be used. How it is? Very easy. You go to the control and simulation, control design, and I think at the stochastic side here, it could be, no, it is not here. Anyhow, if you have forgotten about it, you can, through the help of LabVIEW, check where it is and how it works, or you can just click here, go to the help directly, and there you will find the Owing palette. The Owing palette, discrete linear systems functions. So control design. Now, state space feedback. No, stochastic. It should be somewhere here. Discrete. This is the stochastic. No. Discrete, here it is. Discrete transfer function. This is the function of interest. Now, so the state space model is converted to a discrete one. Now I want to give an input, u of t, to the discrete transfer function. Here it is. This is the input, u of t. And this input really which goes to Kalman filter also. The output of the system here, which should be noisy. So this is the output. I have taken the output and added a noise by Gaussian white noise waveform to it to be realistic and stochastic, and fed this noisy output of the system to Kalman filter. So now we have two inputs to Kalman filter as required, u of t, or if it is continuous, or u of k if it is discrete, and the noisy measured feedback y of k. Having these two signals now, the system will give the estimated output y hat of k. Now I have taken the input u of k with the output estimated of k, with the output, with the input with noise converted also, and all of them are fed to a bundle here so that I can watch the whole picture together, how they change the three expected outputs, the input u of k, the noisy input y of k, and the estimated output y hat of k. If we go to the front panel, here is the indicator. Now, what is there? Let me go back. I am connecting the input as a DC or constant value here with a given noise equal to 0 from a side input. This is not from the feedback y of k. This is the u of t or u of k, and it is clean usually. So I put the error there, or the noise equal to 0. Now, If I run the program, so I shall have a constant output, which is similar or about the value which is given here. Here the value is given as 2. So if I run the program now, it is rising up to 2. Now I have the 3 outputs. The red one is the noisy feedback which comes from measurement. The green continuous line is the input which is without noise, and the estimated value of Kalman filter, which is the white one. And you can see that really it is refining the reading and making the things more accurate. Here is the instantaneous step values of the estimated output. Let us go and change the input to be a different function, not a constant value. I have furnished here to have a sine wave, so I have to disconnect it from here and connect the sine wave. Now I have a sine wave fed to the model as a transfer function and fed as an input, clean input. Here it is, to Kalman filter. Now the output of the sine wave will be also a similar sine wave with added noise, and this will feed Kalman filter. So the output here is expected to be also a 3 different or close to each other sine waves. Let me clear the chart, and now let us try to run it and see how the system works. So as you see, the system is rising up to the value of 2, the maximum value of the sine given here as 2. Yes, and now it will begin decreasing to the -2 and continue oscillating around that. Okay, now let us change the amplitude of the sine wave from 2 to 1, for example. I prefer to stop it and change it. Okay, run it now. Now it will go up to 1, about 1, and will begin decreasing. Why it is 2? It is still 2. I have done something wrong. Yes, it is. I have changed the 1 here and now not there. Okay. It is not multiplied. It has to be must be multiplied by the dial here and then fed to there. So let me multiply it. Numeric multiply. And now I feed it to the plus here, 0. It doesn't change anything there. Now, let us clear the chart and try it now. It is going up to 2. Yes. So everything is okay. Okay. So with this, I have explained to you 2 different control design based programs. In the first one, we created an estimator model by using Kalman filter again, and then we utilized that estimator to find the response for a given input. The second example, we used discrete Kalman filter and configured this Kalman filter externally and furnished the necessary input and the feedback y of k, and have got as the output the three expected responses for a unit step or for a sine wave. With this, we finish today's lecture. We shall continue our work in the coming lectures.